start that recording and start that stream.
No, it's recording at a higher rate.
Yes.
So, okay,
Yeah, it's
yes.
recording at the 1080.
Okay,
So that's good.
When
Okay.
you get home, you can upload
And we are good to go. We're in the green. Welcome to Horsin Around, a dumbass cast. I'm your host as always, Nick Bergadante, and on this very special New Year's episode, I have one very special guest with me. If you'd like to introduce yourself.
Hi, everyone knows me. I'm Andy Potter. We're at Brandreth. We're struggling with my miserably horrible satellite internet, which is hopefully within its last 2 weeks of life here.
Mm-hmm. Yeah, we should.
Fingers crossed.
Yeah, so if the imagery looks like 2 pixels going back and forth, we apologize, but I am recording this in full 1080, so we should be fine on that front when I upload this to YouTube. But yeah, so I've wanted to do this for a long time because our friend Andy here has always had a knack for storytelling and just being an infinite well of knowledge on every science and technology and otherwise related subject that you could just pop into his head. So, I figured we could just go over what we've done this year, what kind of things we're looking forward to in the new year, and yeah, see where the winds take us. But how was your 2021?
My 2021 was pretty full of activities, both with CSH here at Brandreth and with my work. I will spare you the ugly details of spinning IBM into 2 companies and keeping them both of them running at 100 miles an hour. Mm-hmm. People have heard me talk about that. Just go Google a company called Kindle.com, and we're building it while it's operating. That's all I can say. But as far as Brandreth, it's been an interesting year.
What is Brandreth for those of us that may not be initiated?
Oh, okay. Most CSHers who have been around for a while have at least heard about Brandreth or have been here multiple times in many cases. Mm-hmm. For those who are new to understanding it, it is my seasonal home in possibly the most remote portion of the central Adirondacks, which is one of the most remote areas in the eastern United States. We are about 20 miles from the nearest town. We are off-grid. I am powering this electronic gadgetry that Murky has placed on my table via solar-powered electricity. Yeah. And right now, as we mentioned, we are using my tremendously horrible, absurdly expensive, highly data capped, very unreliable. I'm thinking of more adjectives. There's a lot, but satellite internet, yeah. Which I am expecting to fire as we turn up fiber to the home in here. 20 miles of fiber have been installed in the ground. We're still waiting on some final hookup services, power for some of the infrastructure out in North Point of Racket Lake. But that, they're saying, may happen in 2 weeks, at which point I will have better internet at home here at Brandreth, at my second home here at Brandreth, than most of you have anywhere, except for RIT. Obviously, RIT is nice and fast.
Right.
But that said, this is a very remote cabin that's been on a large lot of land up here, a large property of land. That has been in my family since 1851, and my extended family. So yes, I know people up here who are my fifth half cousin, twice removed. Okay. And they give me a big wet kiss at our meetings, and who are you anyway?
Who the hell are you?
Yeah, that's this extended family, but we do go back to Benjamin Brandreth buying this property. Before the Civil War, he was a successful entrepreneur who had immigrated from England and made a fair amount of wealth. And then, unlike a lot of other property holdings in the eastern United States, our family loved this particular lake and property well enough to actually organize ourselves to keep it intact with a stable governance process. Mm-hmm. We self-govern this whole shared property, very similar to the way CSH is governed by its e-board. We call it our e-board, our council, It's a chore we all have to serve on periodically, volunteer, that kind of stuff.
Yep.
But we're here, and there's a lot of homes, and a lot of CSHers have enjoyed coming here over 40 years since I've known CSH. Although I built this cabin myself, professional help, but in 1993, and I've been hosting CSHers in this cabin since that year. So that's a summary of Brandreth.
Yeah, it's truly a lovely. I've been in love with it since the first time I came here in my freshman year from RIT with Computer Science House. And now I'm here for New Year's. We were here in 2019 with a few more people before everything went to shit. But I had nothing else going on, so I decided to roll through, and it's always been a delight, never disappointed. So we were out last night in Potter's hot tub, wood stove, fire powered, which is just the best. And we were ringing in the new year with American Pie.
Again.
As one, yeah. Well, I'm determined to make it into a tradition at this point.
Yep. Only Nick and me, because Omicron kind of put a dent in other guests here this trip. But that's life. We had it. One nice thing, we unfortunately COVID has canceled the last two big CSH fall camping events that we usually do in early September after the kids have spent a couple of weeks at college. And 2018 and 2019, before COVID, were really large events with over 90 CSHers here. We have not done it in 20 or 2021. But in lieu of that, in 2021, I've had a series, and I was looking through my guest book, which everybody who comes here must sign.
Legally required.
Legally required. Penalty of death if you don't. But small groups, pretty.
The legs.
Oh yeah, small group. I'm nervous. Twitch
it's all
kind
good.
of guy. Twitch. We're on Twitch anyway.
We are on Twitch.
So anyway, the a lot of small groups over the year, pretty much from May of this year until even 3 weeks ago, I had a small group of CSHers up on a wonderful trip in here and enjoyed it with them. And all sorts of outdoor activities. Play in the snow or no snow, as it's been a lot. We do have snow here, but it's actually melting again today, a very warm day.
It's been a very warm week,
It's been very warm week for up here. Normally this time of year, we're in the heart of winter. You have a couple feet of snow and overnight temperatures, single digits, and daytime temperatures maybe in the 20s, sometimes lower. But that's where we are up here in this remote, high elevations, wilderness.
We're about you were talking about how after probably into January into February is where you're going to get the deeper freezes.
Yes.
Things are going to get a lot colder before start warming up for the spring.
Yeah, we frequently have spells, and again, climate change is changing this. But we're last few years we've had definitely milder winters than I've ever experienced coming up here for decades in the deep winter. But we typically on an average winter will have a week where every night goes down to anywhere from 10 below to as low as 35 below. I've seen it up here, Arctic level, cold levels, and then the daytime highs may peak out around zero. From any time from like mid-December till late February, you can get those spells. Again, the last 3 years we've had a lot less of those. My recording thermometer is the coldest it's reported up here since November 1st is 0 degrees. So there have been some cold spells, but not super cold. The main body of Brandreth Lake behind us is partially frozen, but the main body is still wide open, as it often is, because it's a deep lake with a lot of thermal mass to cool down.
200 feet?
to about close to 200 feet in its deepest spot. Out in front of us, behind us, is thin ice, and of course, Nick and I continued a tradition that that some CSHers 3 weeks ago did. Is we plunged in, we cut a hole in the ice and plunged in and did a polar plunge before running up to the hot tub.
Yep.
That was an interesting experience yesterday. If Devin Mate ever watches it, I did wear that hoodie. He does owe me another $150.
Tab's running.
That's the deal.
So what I was originally expecting because it's been warm, and I was expecting that lake behind us was going to be just open water at a certain point, because I thought it was going to get warm enough for that. But Potter did not just deem to remind me on our way down that was probably not the case. I thought I looked out there, and it's still, sometimes I look out this window and it's kind of looks like it's watery more than it is ice, but you get down there and it's still a lot of ice. So I was planning on just jumping into some really, really cold water and then immediately sprinting out. But what happened instead was Potter took an ice auger, broke a giant hole in the ice, and then I had to lower myself into it after he dropped himself into it, yeah. And then I decided it'd be a great decision to run back up to the hot tub barefoot. And it's probably it's a decent hike when you're wearing next to nothing and freezing. So that was not the greatest idea, but we did it.
He wanted to do it, so we did it. And I wimped out 3 weeks ago when the other CSHers went in the similarly cold water, although it was open then. But 3 of them went in and also ran up to the hot tub and warmed up quickly. So, it's sort of a little polar plunge challenge that we've done up here. I haven't done this in years, but I did it this time and woohoo, survived. The ice is still pretty thin. We wouldn't trust walking on it there in front of us. Yeah. And what it is there's sloppy water on top of it because the air temperature is above freezing. Even now it's above freezing. It's like 39 degrees Fahrenheit. Mm-hmm. So you're getting the snow that was on the surface making a sloppy water layer on top of about 1.5 inches to 2 inches of ice. Which is not safe for going out. And we didn't go into deep water. We were in thigh deep water when we did this little plunge yesterday. Yeah. So we weren't going to die. It was an uncomfortable event, I'll give you that.
Yeah. The other thing I was going to mention is that you were expecting this that fiber internet you were talking about earlier to be in by now, but the company has kept fucking you over, as it were.
Well, there's been all sorts. Well, actually, the fiber installers have been doing their part, and they've got it in. They got to do some more pedestal making, but they've done all the splicing except for the connection to me. Mm-hmm. But that's not the issue. We found out yesterday from one of my cousins. We drove by them on the road. They were leaving. Yeah. That out at North Point, which is it's about 8 miles away, and it's a summer hamlet of homes where they actually have utility power out there from NYSEG is the power company, mm-hmm. And Adirondack Tech, who is putting in this fiber, has installed a powered GPON, you can Google it, gigabit passive optical network. It's a fiber optic networking system. Verizon Fios uses it. They have to put a cabinet in there, and it needs to be powered. So they install the cabinet next to one of the power utility poles, which is out there at North Point for those homes out there. And they've got the cabinet built, and they've got the meter and the electrical wiring in place, the meter box. But NYSEG, the power company, was supposed to, 2 weeks ago, actually put a transformer up on the pole to give it power. They haven't. And the reason they haven't is I found out that they told Adirondack Tech, you never paid us to do that. Adirondack Tech pulled up the canceled check from their banking files and said, yes, we did. And this was like a week ago or so. And then they said, well, all right, we'll come out in 2 weeks. And so no power, no internet. We're not here yet, but maybe 2 weeks from now, I may be back here with much better internet than this hard-looking horrid satellite internet setup, I have not.
Yeah, but you've been able to scrape by on it for a lot of years now, right?
Yeah, I've had HughesNet and Viasat now for coming up on 10 years up here. Prior to that, we had wireline telephones from a variety of phone companies that keep going bankrupt up here and then getting bought out by somebody until they finally abandoned us in 2016. And the latest one was Frontier, our lovely Rochester-based phone company that really is dying on the vine. But they abandoned us in 2016, and the wires, a lightning storm destroyed them, and we had no communication whatsoever. And people could not depend on satellite internet for reliable communications for emergencies and things. And that's what made us dig into researching what it would take to bring in reliable fiber optic based internet. And after a lot of bureaucracy within our organization, we approved it, and the installation is happening. So that's where we are.
Yep.
Stay tuned.
Yeah, so what kind of stuff do you have in mind for 2022? Now that the new year's in, do you have any resolutions or anything like that on your mind?
Well, I have a lot of personal things I'm working on. Obviously, my work is still very intense, and I'm spending a lot of time, I've always worked home office. For the last 15 years, I've been home office with occasional forays to IBM campuses where I work jointly with the IBM team and our AT&T team to build and manage IBM's global network. So that's going to keep me quite busy over the next year. But as far as personal, I have plans for both my home in Rochester and here. One of it has been an ongoing project, which Nick started out in helping over a year ago in September. Is behind us. I don't know if you see it in the screen.
You can barely see the roof behind us. It's kind of blown out with the lighting, but you can see it
of the gazebo we've been building, and it's been a COVID project for over a year. It has the structure and the roofing is done, and a lot of CSHers are to be thanked for the effort that they volunteered to make this thing happen. I'll name people like Zach Jackson, Dylan Jackson, Matt Campbell, Matt Bonnie came in and helped, and innumerable others. River, Connor, I can't even call the names out. So if I forgot you, slap me on the face and tell me. But I'll have to go look in the guest book. But so many have come up on these small trips this year and, help me build this thing and improve my solar power setup as well, so that I will have more reliable power, my off-grid solar power.
Yeah.
Although this time of year, when it's cloudy and foggy, you don't get a lot of sunlight to drive solar power. And so I've got a little portable generator helping us right now on this very foggy, dark January day. Day. So.
Yeah, it's you gotta really work for that rate of return on solar power, it seems. You gotta get the good sun angles, which are mostly in the summer, and then you've gotta have them, highest point in the sky, like during noontime, and all that stuff.
You've got to orient your panels. You've got to have sufficient battery storage for overnight, and the goal with an ideal off-grid solar power is you always get enough solar power during the day to supply not only your usage in the night, but to recharge the battery the following day for the usage you do overnight, so that you don't start in a deficit each morning. This time of year, it's actually very hard, and in fact, with the size of most solar systems, not possible. So we do supplement our winter or really long cloudy day types solar with generator power to have a complete full powered house, which this is not. We have propane gas lamps and propane refrigerators and propane water heaters that do a lot of the utilities. Some of the gas lamps, can you see it here? Yeah, up here on the right, there's our propane gas lamps that do my day-to-day lighting. But as I am, moving into, going to be using this more as a home office, I'm going to be, need more, PC support, monitor support, and some electric lighting. LED lighting is definitely better to use because it's lower power, but So my day-to-day power usage is increasing as I'm going to be spending more time here, and with the fiber internet, doing a lot more telecommuting here, and hopefully in a situation where I can then move out and renovate my house home in Rochester, which is overdue for a lot of renovations. And as long as in the round of renovations I want to do basically is move out, put all my stuff in storage, and kind of gut it and redo it. So that's going to be another project coming up over the next year, based on when I get settled in here as an alternate home base. So that's where we are.
Yeah. So I mean, I would envy you to no end to be able to just live and work here. So that's a pretty sweet setup that you're gonna have once you get that fiber in and start the renovations on your place back in Rochester.
Out of curiosity, can that video we took yesterday of the going in the lake be added to this or not?
Not live. No, I still have it on my phone, so I need to get it over somehow. But I'll put it up on, at least for Computer Science House people, on Gallery. Maybe I'll put it up on YouTube. I think for me, it's definitely like you were talking about your quarantine project being that gazebo. This has been it for me. I mean, the podcast I've been doing since 2019, the fall of my senior year. But then as that evolved, and then COVID hit, it's just been something that I've been able to keep myself busy with outside of the schoolwork and then the full-time work that I've had outside of that. It's a nice hobby to have. So I'm hoping I can keep this up and make some more content that people enjoy. I've been having a lot of fun doing it. So having done like the game streaming stuff for over a year now, I think it's bodes pretty well for seeing more stuff in the future. So I hope you guys look forward to that. But let's see. What have you been reading about lately, Potter? What's some science stuff that you you were talking to me about the multiverse theory that you were looking
quantum
into
theories of multiverse, which I'm sure a physics major or somebody will know a lot more. But I anyone who knows me is I'm a science and history nerd, and I just vacuum up all sorts of science information as fast as I can, and probably to the dismay of a number of people around me, spew it back out at
you regurgitate it at lightning fast speeds.
Yeah. But hey, it comes with the territory. If you're gonna come here, you're gonna get some of that stuff. So I am fascinated in astronomy. Something that really got me involved, obviously, the onset of COVID, really got me into fascination of microbiology and the science of pathogens. And those of you who have followed, my experience through the COVID process, including my early involvement before vaccines were available, starting in mid to late 2020, joining the Pfizer clinical trial and participating. I'm still actually participating in it, although I was unblinded and they offered me full vaccination. I was actually a placebo member of that trial, so they gave me fake vaccine, basically saline. Back in early November 2020, before they was approved, and after the EUA approval in December, they called me and says, you have the option of being unblinded, and if you are a placebo, get the real vaccine.
The real thing. Yeah.
And I got it. So, but then as a part of all that, and really meeting some fascinating people, including the study doctor at Rochester Clinical Diagnostics, which is the Rochester area research lab that Pfizer engaged to run our regional placebo. And they had 44,000 people worldwide participating in this trial. to get that vaccine developed by a German company called BioNTech. But Pfizer, being a massive pharmaceutical, put together their medical manufacturing and scaling capability to get this thing out to people faster than ever before. I will say though that fast doesn't mean safe. The underlying science has actually been studied for over 10 years of mRNA vaccines and mRNA medical treatments, which are actually in the pipeline even now. There are going to be some really interesting announcements related to cancer treatments using mRNA technology. But I'm not going into the nitty gritty. I will say that it has been a phenomenal learning experience for me, including an hour discussion I had with this study doctor at Rochester Clinical Diagnostics, who spent an hour. He's just a science nerd about biology. He's an MD doctor, but he's a research scientist and not a medical doctor like practicing and taking patients. Yeah. That's his thing. And he really got me interested into that, and I've basically been interested in that science ever since. And probably to the dismay of people around me when I talk too much about it, but that's just me.
Do you think the I'm not sure if it was related to mRNA or something else, but because of its ability to sort of rewrite or write genetic properties or whatever, is that going to bring on the advent of designer babies and that kind of stuff? Is that something that is related to that? Or
actually, no. Else? No. mRNA is a string of genetic material like RNA is. Okay, yeah. RNA is a little bit of science here. Sorry, you asked it. Is half your DNA. Half your DNA is a double helix of genetic material that describes a protein or something biological. It's the blueprint for every living thing. Is DNA, but RNA can be a blueprint for things that aren't quite living, like viruses. Mm-hmm. Viruses are not technically life because by themselves they do not have the mechanism to reproduce on their own, like a bacteria or a living cell or algae or pretty much everything else. Viruses just have genetic material, and they hijack the cellular structure of living things like us to reproduce. And so that's RNA inside a pathogen. RNA and messenger RNA is actually what I use the term work orders that your DNA does to make every protein that you have in your body, which from fingernails to hair to skin to muscle to boogers, those are all proteins. Albumin is a protein. Egg yolk is a protein. All these things are manufactured using a blueprint in the DNA. But the DNA hands out a work order, which is called messenger RNA. And that does all the heavy lifting to make you replace cells, grow up, everything, okay? And so what these vaccines do is they provide a messenger RNA to make fake pathogens, which are these identifying, well, in this case, spike proteins for COVID, but it could be any kind of protein for any kind of pathogen, really. And it uses your bodies to make those, but it's not making the virus. And it's not, messenger RNA is built in such a way, it's been in every living thing since the beginning of life, is not, does not become part or modify your DNA to make you a monster, okay? Because we have literally, there's just so much messenger RNA in every single cell of our body that's just enabling us to live. This is one we're saying, well, you've got the whole factory that knows how to use messenger RNA to make it. Why do we infect you with, other vaccines use what are called viral vector. They take to modify one type, they modify a weak common cold virus, an adenovirus. A chimpanzee-based adenovirus is how the J&J or AstraZeneca one works. And they modify it to make these same proteins. And you get infected with it, it's mild, you don't really get sick at all, but it makes these proteins that look like coronavirus, and your immune system goes, oh, I gotta defend against that, and it builds the infrastructure and antibodies and memory T cells and B cells to defend itself. And now your body's kind of armed up to defend the real pathogen if and when it shows up. And all viruses do that. And as I've said, the whole all vaccines do that, and that's how they work. They use different mechanisms to produce that fake pathogen proteins that trick your immune system to responding, and your immune system then learns. And that's the science. And there's tremendous other stuff that I've learned, and I could probably waste 3 or 4 more of these podcasts talking about it, so I won't. But reach out to me if you're interested, or go read the Coronavirus Slack channel if you're a CSHer.
No, there's tons of resources out there, and you're just absorbing so much of it.
You're about almost knocked it over.
Okay.
Light over.
But yeah, so but we got off of the I wanted to talk about that multiverse thing that we were talking about the other day. You were the way you described. I will try and recall how you described it to me, and you can correct me if I'm wrong. But basically, people are not sure how dark matter and dark energy exist in our universe, and so there is a theory posited that the multiverse exists, but it is it's a Schrodinger's box type situation.
Well, Schrodinger's cat. Okay.
Every cell or every atom in the universe,
every
subatomic particle is being shared between an infinite number of multiverses all at once.
And so so in other words, the idea in quantum mechanics, and this is just theoretical, okay, obviously. And there's a lot of ideas to try to explain the behavior of quantum mechanics. Some is well known, and in fact, there's technologies made out of it, like tunneling diodes can use quantum mechanical effects in electronics, and we do it all the time.
Is that different from quantum computing?
Well, quantum computing, I have to go back and actually spend some more time. Quantum computing uses quantum behaviors to create sort of a dynamic approximation of knowledge in such a way that it can solve problems that traditional computing can't. And that's as far as I'm going to go before I go find a book and read detailed into it. Because honestly, you get into this stuff and the math goes, so I'm not going to try to posit any real kind of understanding of quantum computing, but I will sort of understand explain my understanding, which is, and you can just go Google Schrodinger's cat. Schrodinger made a thought experiment about, one thing that is sort of a quantum event is the radioactive decay of large atoms that are not stable with their neutron proton counts. They decay into other elements or lose neutrons or electrons or things like that, or protons and things like that, and become other elements over time, like radioactive uranium or plutonium or radon or all sorts of these things. They can predict their half-life, but they cannot predict when, in fact, the exact rate. Like I have a single atom of uranium-235, half-life of 700 million years. Okay, uranium-238, 4.5 billion years. Somewhere over there, if I have a whole lot of uraniums, about during that period of time, 700-something million years of uranium-235, half of it will decay away into an element other than uranium, on average. Okay, but to pick one average atom and look at it and say, it's due to decay next week, impossible due to quantum theory. Okay, it's to predict. And so quantum mechanics, and is it Erwin Schrodinger? I can't remember his first name. Anyway, this physicist posited that he had a radioactive element in a box, and it had a decay rate, a maybe very slow one. So like his theoretical radioactive one, it had a decay where it might spew out a proton or neutron every few hours, really. But until it could do it from the minute you close the box up, and when it does, some kind of electronic detector will detect that decay, and he puts a cat in the box. And it will release, when that detection happens, cyanide will kill the cat. Okay, it'll release cyanide and the cat will die. And the problem is in quantum theory, Schrodinger's theory basically says, until you observe
the dead
cat, it exists because its life or death depends on whether or not a quantum event such as a radioactive decay occurs in any given period of time, which it could occur from instantaneously the minute you put the thing in the box to, millions of years, okay, just randomly. On average, a lot of them would occur over what we call its half-life. But, so in that state, it has both occurred and not occurred. And therefore, until you observe the cat, it's both alive or dead.
Yeah.
And it's technically impossible to predict its state until you open the box and look at the cat. Okay, okay, meow meow, or dead. Okay, and now you know, but you've observed it. And one of the things about, and of course, the Millikan electron dot experiment, you probably did, electron particle, weighing electron, is when you shoot electrons at not a Millikan experience, I'm sorry, that's a different one. When you shoot light photons at a very fine grid, a polarizing grid, you see light behave either as a particle or as a wave.
Right.
But once you observe it, it's not the other. Okay, and so the quantum effects of a photon, a single photon of light, for example, if I shoot one photon at a grid and I look at a pattern behind it, I see waves.
Yeah.
That implies that the photon went through two slots in the grid. There's only one photon. Whereas if I actually have a photon detector, I will see only one photon come through.
Yeah.
And that's quantum mechanics. That's also a high school experiment you can actually do. And that's also, one of the fundamental supporters of quantum mechanical theory in physics. And I'm getting close to my limited knowledge of this stuff.
Yeah.
But the metaverse I read about is the idea is
not to do with the Facebook thing.
Forget Meta. They ruined a good thing. Okay, like a lot of things. Anyway, the
metaverse,
the side thing. When Metaverse, the company came out and they announced their name change, New York Times printed a photo of their sign. They unveiled their new sign. And conveniently in that photo, there was a guy walking along with a trash can and a trash picker up right in front of it. So it looked like somebody was taking out the trash with the new sign behind it in Metaverse. So that was I think that was intentionally done by some reporter for the New York Times.
Cheeky.
Back when they announced it, you could probably go find that photo on their website. Anyway, But the metaverse is the idea that until you observe a subatomic particle, it could exist in all states at the same time. And therefore, with an infinite number of universes, if I extrapolate that, there's one where I pick up this cup or I didn't pick up this cup. And there's no way us living within our field of view would know, are we constantly switching based on our decisions and we have no knowledge that our same subatomic particles didn't pick up the cup or did pick up the cup? And that's sort of the theory of it. And one thing I read, and I'm trying to remember whether it was a New Scientist article or somewhere, I can't remember, or somewhere online, is somebody positing the idea, and not none of this is science, so I'm going to just say it's very speculative. The idea is that that subtle imbalances in quantum theory mean that when you have quantum different behaviors based on quantum go left, go right type things, or whatever, or go this way or that way, or kill the cat or not kill the cat, there's not 100% stability of energy and mass, and this writer posited the idea that might explain what we observe, which is still a major mystery in astronomy, and the James Webb Space Telescope is going to try to look further back into the time of our universe about the formation of it.
It's looking back in time.
Well, so the James Webb Space Telescope is a very powerful telescope that's going to look at infrared way away from the Earth. It has to go away from the Earth. And when you look at things far away, it could, like the Hubble could see galaxies like 13 billion light years away. So it's seeing galaxies that are 13.5 billion years old. Our universe, based on the expansion theory, is predicted at being 14.5 billion years old. Okay, our solar system's at 4.5 billion years old. So these are enormous periods of time. But the idea is, if I have a more powerful telescope, I can see galaxies further away, okay, and therefore see them younger and look at their behaviors, like what kind of light is coming from them, the stars in them. The earliest stars that formed right after the Big Bang. The James Webb will be able to see much further back in time, because whenever you look at anything in space, you're looking back in time, because light comes from those things at a fixed rate. You know, and so if it's 13.5 billion years, light years away, which is a distance measurement, you're seeing something that happened 13.5 billion years ago. And the James Webb could push the 14 billion, maybe more, by looking at infrared. Why is infrared so important in space? Because the dark energy is predicted to be the force that's causing the universe to expand faster and faster. It's pushing really distant galaxies, not nearby galaxies. Andromeda's still going to crash into ours in probably about 3 billion years, and it will make a big super galaxy. But that's not that. It's close enough that it's falling towards us. Gravity is overwhelming that. But really far away galaxies that we observe, you can see redshift, meaning as it's moving away faster, the wavelength of the light from those stars gets yellower and yellower and redder, and ultimately disappears and it goes into the infrared. Because it's going so fast, the wavelength of the receding device gets longer, and therefore you can't see the visible light. So if you want to look at the spectra, which defines, what element is making this light wave, okay? Spectroscopy is, just basic physics, not even quantum mechanics. And that's how we can look at a star and say, that star has this much hydrogen, this much helium, this much oxygen, this much iron, all this stuff. They can see ionized gas spectra. When you look at a fluorescent light, you're seeing the spectra of ionized mercury vapor in a fluorescent light. But glowing, okay? Yeah. And neon lights have a different gas neon, neon light, and it glows red, and that's spectra that you see. But those spectral lines can identify the element that is ionized. By ionized, you basically you either heat it or you put a powerful electric charge in it, which is what fluorescent lights do, and it shakes the electrons off the atoms. And they kind of throw fleetly in there, and then when they come back and reconnect to that atom they want to be part of, they emit energy, and then the energy from the electric field or the heating of it shakes it off again, and they make it with particular quantum spectral lines that observe. And that's how scientists have been able to determine the chemical makeup of anything that glows in space, okay? And that's really useful. Yeah. So the James Webb Space Telescope is going to be able to see into the infrared, and therefore see the spectra that's so red-shifted due to the Hubble expansion theory, and it was Erwin Hubble. That's why the Hubble telescope was named after him. Mm-hmm. He was a scientist who figured out that the most distant galaxies in our universe are accelerating away. Yeah. And the force that's moving them, they don't know what it is, and they gave it the name dark energy. Okay? Right. Okay. So that's why, we all hope this James Webb telescope unfolds its complicated. Infrared is hard to see.
Is it going to be in space, or is it on Earth?
No, the James Webb Space Telescope was launched from the European Space Agency in Guyana in South America on Ariane 5 last week, actually Christmas Day morning, and I watched it, I streamed it up here. And it's a very large space telescope, very different in design from the Hubble. The Hubble orbits the Earth, okay? Yeah. And it has very clear visibility in optical things with a big mirror. But this mirror on the James Webb is huge. And because it primarily wants to look at infrared is heat. It's near a really bright sun. Yeah. And so it has this really complicated sunshield that, in the vacuum of space, unfolds and insulates the bright temperatures of the sun from it. And they, because they want to be, it's so big, and they want to be away from even infrared reflecting off the Earth, they're shooting it to a spot 1 million miles from the Earth.
Yeah.
Okay. And it's what's called a Lagrange point, where it'll actually be kind of orbitally stable, just kind of trailing, or I don't know if it's trailing or leader, but L2, L5, L2, it's somewhere, what L1, L2 Lagrange points are kind of stable areas when one body orbits another, like Earth orbiting the Sun, Jupiter orbiting the Sun. There's these spots where if you put an object, like an asteroid or a spacecraft, it will kind of want to stay there. And the James Webb wants to be there because it's so expensive. Unlike one that they have in orbit, like the Hubble, they used to service and add, service it so they could keep its orientation, and they use the shuttle to put it back up. They can't do this with the James Webb, and the only way to keep it in spot outside of putting it in a Lagrange point would to have a large amount of thruster fuel that would run out. And being a million miles away, we won't be able to send people to fix it or service it.
Right.
So they're putting it at a Lagrange point so it will stay there without the use of thruster fuel. And to point itself, it will use basically gyroscopes, okay? Inertial spinning wheels. And the Hubble does that, and that's how it aims itself. But that doesn't move it, that just orients it, and they can very accurately focus on any part of the sky it wants to.
Yeah.
Obviously, it can't look at the sun, and it's designed to keep its big, complicated, really thin mylar folded up Sunshield, a really complicated one.
But I would assume it still has some solar powering those.
Oh yeah, it has solar panels. It has solar panels that are visible to the sun, and that's out in space it never sets, so it doesn't even need a lot of batteries. It's because maybe it needs some. If I don't know how the solar panels. If it's twisting away to look somewhere else, maybe it's not going to orient the panel, so maybe it has some batteries in there. But ideally, maybe the thing can point, and the panels can stay pointing to the sun. They're outside that sun shield. Okay. Mm-hmm. The whole purpose of the Sunshield is to keep the optics of this really large telescope arrangement that also has to fold up because the whole thing wouldn't have fit in the rocket. Okay, so this thing is in the process of origamiing into this really massive thing. These Sunshields are the size of tennis courts, sprayed out on these mylar sheets behind it, and it has hundreds of little pulleys and things that to deploy these really thin, lightweight mylar sun reflecting things in the vacuum of space. That means the optics can be at hundreds of degrees below zero, which is necessary to detect infrared in space. Yeah. So that ties, and so it goes back to our whole metaverse. Is how did our early universe in the time of the Big Bang, where theoretically all the energy, mass, and everything started in a point source and kind of exploded out. Yeah, in the Big Bang Theory.
What would even have brought it to blowing out in the first place?
We don't know.
Because mass would generally, you'd think, stay.
Yeah, that's right. But there's lots of theories that are extremely speculative. The brain theory. Maybe the multiverse theory with imbalances. One of the interesting things is the science of high energy. Let's say I have a tremendous amount of energy, like trillions of degrees, which might be what you would have in something as big as that. When it cools down and actually makes atomic particles, okay, physics says, traditional physics, not quantum physics, says it should make antimatter and matter. Remember, antimatter is the opposite of matter, where a proton would have a negative charge and an electron would have a positive charge.
Oh, what the hell?
Yeah, that's antimatter.
Okay.
And if an antiproton touched an regular proton. Remember, opposite charges attract. So, they annihilate themselves in 100% energy production. 100%.
Yeah.
Even the nuclear reactor, which uses fission.
But matter shouldn't be able to be created or destroyed, right?
But no, it gets turned into energy. That balances the equation. Okay, energy. Okay. So matter can be converted to and from energy, and we do that. Even chemical energy, microscopic. But when I split an atom or I fuse atoms, the weight of the product of fission or fusion is a little bit less than the original one. And when I actually fuse them, if there's something I want to make a really fused one, I have to absorb energy, and that makes it balanced. Okay, and that actually is proven. Okay, supernovas, which are massive fusion events to make heavy elements, actually have to suck energy out of the star. But the energy, this collapsing star has enormous amounts of energy, and that's how it makes heavy elements. But the equation's always balanced. But one of the things about matter versus antimatter, and we've made, tiny, infinitesimal, like a few anti-atoms, if you will, like a few in labs. But it's incredibly hard, take like more energy than we could possibly produce to make enough antimatter to power, the Starship Enterprise. Okay, which if you remember, Starship Enterprise is powered by antimatter, and somehow they in sci-fi land they've managed to make.
Can antimatter be used as an energy source?
Oh, if you could control it, contain it.
Yeah.
But remember, antimatter, an antiproton is. Protons have a positive charge, okay? An electron has a negative charge, okay? And we use that all the time to make electricity happen, and static electricity makes your hair stand on end because like charges repel and opposing charges attract, okay? That's basic electricity, static electricity, the whole thing.
Yep.
But an antiproton and a regular proton have opposite charges. They will attract. They will go boink and touch each other, and the mass, atomic mass of one proton versus an antiproton, they have the same atomic mass, and they theoretically have the same characteristics, other than that just their charge is 100% reversed. But when they touch, they consume themselves and produce the electron volt equivalent in energy, and that's actually a little gamma ray burst. Okay, well, if I just touch, it'll be pretty small. But obviously, if I happen to have and somehow happen to be able to hold it in hand in a magnetic bottle, so it's in a vacuum, so it doesn't touch anything, antimatter, and I open up my magnetic bottle and I have just a hunk of regular matter of equal mass, and gravity should still work on antimatter. Gravity is there, so they would fall, and if they touch, if I had a pound of it, it would be 100% turned into energy. And that would be more powerful than any atomic bomb we ever exploded because it's 100% efficiency conversion to energy. Now, we're nowhere even close to being able to produce something like that. But the theory of the universe should have said the universe should have been created with equal, and Stephen Hawking actually wrote about this in Brief Theory, the first 3 minutes, and also the Brief History of Time, on how this is a big question on the formation of the universe. When there's just yearly Big Bang mass, it's nothing but just confined energy and no particles is the one idea.
Yeah.
And when that energy kind of bangs itself out and cools and allows atomic particles, subatomic particles, quarks and other things, and then they assemble into electrons, protons, should have produced equal amounts of antimatter.
Yeah.
And therefore, it should have, you would see maybe antimatter galaxies, but you would see equal amounts, or they would just annihilate themselves back into energy. And by all indications, everything we've observed in our universe is all matter. We don't know why. And anybody who says they know why is lying. And so but maybe it ties into other things we don't know, like dark energy or dark matter. Dark matter is there's potentially more dark matter than real matter. Real matter is stuff we can see, stars.
And that's different from antimatter.
Dark matter, it could maybe. There's an anti-dark matter, okay? But all we see is matter, and what we can't see dark matter, but we can see the effects of dark matter. So, for example, we can look at a galaxy and look at everything there, and we can actually posit that there is actually a supermassive black hole, in the center, okay? And then you see stars, and the stars are orbiting the center of a spiral galaxy, just like the Milky Way and the Andromeda, which you can see in Cassiopeia in the sky at night. Anyway, that's the nearest big spiral galaxy. The rate at which a star orbits the center of the galaxy is a good indication of the mass of the entire galaxy. Just like if I got for example, a big massive planet like Jupiter, its closest moon, Io, is about as far as our moon is from our Earth, but Jupiter is 90 times more massive than the Earth. It goes around like once a day. Yeah. Because the mass of Jupiter means the orbital speed is so much faster for the moons around Jupiter. Versus our moon goes around the Earth once a month. Okay. Now, what they've looked at these galaxies, and again, they can look at the red shift of the light, the spectra from the galaxies far away, and they're saying these stars are moving too fast around Andromeda. Why? There's mass, and the mass is not all at the center because they can actually predict that, hey, wait a second, there's like a halo of mass around the entire galaxy, not at the center. And if they predict, they can say, there's this much mass we can't account for. We can't see it, we can't detect it, we can't touch it, but it's affecting the gravity of that astronomical object, an entire galaxy, and we can see that. And they don't know what it is, and they call it dark matter. Okay? Dark energy is related to the Hubble constant. Why are galaxies, normally when you have an explosion and the explosion pushes stuff away, as they go further away, the force of gravity from all the stuff behind it should slow it down. And maybe you're going faster than escape velocity, so it never slows down and falls back on itself.
Yeah.
But like if we throw something off the Earth at 25,000 miles an hour, forget the atmosphere friction, it will escape the Earth and go into a separate solar orbit.
Yeah.
Okay, but it will continue to slow down the further away it goes at a slower rate, but it will slow down.
Yeah.
Why are these most distant galaxies that the Hubble can see and that the James Webb will see better accelerating away from us faster and faster? The further away they are, the faster they're moving from us. And that's the Hubble expansion content. And that they call dark energy. So two very different things from while we observe their effects.
Yeah.
We're not really observing the energy. We can't see that energy. It's not light. It's not, gamma rays or visible or anything. It's something moving, accelerating away. Okay? And just like dark matter is making, things around galaxies, and actually I just read, they actually did find a galaxy with telescopes that seems to have no dark matter in it. In other words, the math adds up. Those stars, redshift going around that core.
Is there dark matter in our galaxy?
Yes. We're going too fast. Our sun is going around the center of our galaxy faster than it should, based on what we can see. Okay? Now, it still takes, a billion years to go all the way around, but, I don't know, a long time. But our galaxy is about, Milky Way galaxy is about 50,000, about 100,000 light years in diameter, with more as you go closer to the spiral bands. We're about 25,000 light years from the center of our galaxy in Sagittarius. And Sagittarius A is our galaxy's supermassive black hole. And we can actually observe things around it through infrared, where just regular infrared telescopes in space. You really can't observe an infrared from the Earth easily because the Earth atmosphere gets heated up and makes it all foggy and messy. But and greenhouse gases scatter it more, believe it or not. So infrared observing from the surface of the Earth is hard. It's not impossible. If you have a crystal clear sky, you can see some near infrared up on mountains in South America and on Hawaii where it's really clear. But by and large, most infrared observations that we do within our galaxy, we do from various telescopes in space. And infrared is light. It reflects on mirrors and can be focused by lenses and all that good stuff. But we orbit about halfway out in the Perseus arm of our galaxy. I don't know which one, but anyway, we orbit the center of our galaxy, and based on what we can observe in our galaxy, and they've actually calculated the mass of our galaxy's central black hole. Another mystery. How did those central black holes ever first appear? Physics doesn't explain it. Oh no, stars just didn't fall in. Okay, the math doesn't work out. Okay, but it's massive. It's like millions and millions of stellar masses in a physical area about the size of our solar system. So millions and millions of stellar masses. And ours is an average size. There's actually Andromeda's like billions of solar masses in its central black holes. It's a bigger galaxy. And but that central black hole is observable. You can't see the black hole itself, and it's a quiet black hole. There's not a lot of stars being shredded at the event horizon. When that happens outside, they actually release gamma rays, and you can see the effect of it. But we can see by looking through, and there's dust clouds around the center. It's very dusty layers. But in infrared, we can see the stars that are orbiting our black hole. And they are in various orbits, and they can, by looking at the spectra of the stars, they can actually determine roughly its mass and its age. Okay, that's just science of stellar astronomy. But they can also see its rate of orbiting that central black hole. A lot of elliptical orbits and things like that. And from that, they can calculate the mass of our central black hole. Okay, and they have a pretty good idea of what it is. And when they look at other galaxies far away in telescopes, they see those same effects. Yeah. And so the science there basically is saying, okay, why is the outer spiral arms if there wasn't dark matter, our spiral galaxy would have kind of cast its stars out. They're moving too fast. Yeah. Okay, into intergalactic space, and it's not. Okay, that is. They're calling this gravitational force, the whatever's behind it, dark matter. And that's the science there. So yeah, we got heavily into science. Sorry.
No, that was exactly what I wanted to get out of this. So and that ran us to our hour mark. So yeah, thank you guys for watching. Thank you for joining me, Potter. I hope everybody has had a happy new year and is ready to do some great things in 2022. Until then, thank you guys so much for watching. Stay safe out there.
Yeah, have a good one.
Peace out.
We're going to have lunch and go in the hot tub.